So thank you everyone for attending today's AFMS Zoom seminar. We're very lucky today to have Professor Wolfgang Schröder from Aachen University speaking to us. Professor Schröder's done a lot of interesting work in aerodynamics and compressible flows, and he's also done work in biofluids and particle-laden flows. He's had a long relationship with Aachen University. He did his PhD there, I believe, before doing a postdoc at Caltech and moving around to the German aerodynamics department. I'm not sure if that's the correct title, before landing back at Aachen as a professor. He's done a lot of interesting computational work around LES methods and multi-grid solvers and these sorts of things for compressible flows, aerodynamics applications. So we'll be very interested to hear what he has to say about drag reduction today. So thank you very much, Professor Schröder.
Thanks, Dave, for the introduction. And I'm really happy to give a talk from Aachen. And this is going to be a talk from Aachen to Melbourne and to other places. So it's the first time that I don't have to travel to give something like, let's say, an international talk. So like I said, okay, thanks a lot. And I hope it will be to a certain extent entertaining when I talk about wavy drag reduction. And like I state right in the title, I think, okay, that wavy drag reduction works. So, and you can see that this is definitely also joint work together with Marian Albers, who is a PhD student of mine, and then with a couple of good friends, Daniel Vernex and Richard Seemann from Braunschweig, and also Bernd Noack. And Bernd Noack, he moved from France to China now. He does have a permanent position at the Harbin Institute of Technology in China. And Bernd and Richard and Daniel, they did some stuff with respect to machine learning in that area of drag reduction. So the outline of the talk is here. First, of course, I'm going to give you, let's say, a brief motivation why we got interested in it. And then I go to the fundamental flat plate turbulent boundary layer and let you know what we did with respect to, let's say, a smooth and a structured surface. So this is kind of, let's say, another part of the introduction before, let me go back, before I talk about something that is related to how we increase our solution space, you can say, and there we use something like a reduced order model. And then, of course, I'm going to talk about the airfoil flow. And we're going to consider two airfoils. One is the DRA, and the other one is the NACA 4412 airfoil. And if there is time, then I will also briefly talk about what we have done with respect to swept waves. And then finally, of course, some conclusions. So let me come back to the motivation. And of course, okay, this is clear when you consider, say, any, let's say, flying or any other object, you would like to reduce the drag in order to have, let's say, a lower energy consumption. I think this is pretty natural. And it doesn't matter whether you consider, like I said before, an aircraft or anything else, but with respect to an aircraft, you know that roughly 50% of the overall drag is related to friction. And when you consider, say, the various decomposition of the friction part, then you can say, okay, it's 40% that belongs to the wing and roughly, let's say, 60% to the fuselage. Nevertheless, drag reduction is definitely something that one should be interested in just to make sure that we do something good to our environment. And there are different ways, okay, of course, to influence the wall shear stress. And I'm going to concentrate on something that has to do with wall motions. And here I show you on the left on this slide, I show you a categorization that goes back to Tomoyama and Fukagata. And we consider, say, oscillations just, let's say, in one plane. For example, okay, that you do have, let's say, a perfect oscillation, or you do have to consider something like traveling waves in the streamwise or spanwise direction. But when you consider, say, the upper part of this table here, then this means that the wave doesn't have any deflection in the wall normal direction. When you consider the lower part, we do have transversal waves. So we do have a deflection in the wall normal direction. And of course, when there are also, let's say, different traveling waves, for example, the one by Nakanishi, and he considered, say, a streamwise traveling wave. And what we do, and this is the reason why I marked it here by a red box, we consider, say, a traveling wave moving in the spanwise direction. And on the right, you see a movie that will show you what I have in mind when I talk about a traveling transversal wave in the spanwise direction. You consider, say, the flow from the lower left to the upper right, and then when I start the movie, you will see, say, the moving part of the surface. This is shown here. And of course, that kind of movement can be described by a simple function where y is the coordinate in the wall normal direction. And that can be extended, of course, to some kind of vision. What I show you here is the following. It's nothing else but an airfoil. And you see the arrows. And the arrows, okay, they're going to move in a few seconds when I start the movie. And they just show you that there is some kind of flow over the airfoil. And in the upper right corner, you see C sub D, which represents the drag coefficient. And when you don't do anything to the surface, this drag coefficient does have, let's say, a certain size. And then you will see after some time that the surface of the airfoil, that this surface is going to undergo a transversal spanwise traveling wave. And then the CD will be lowered. And this is more or less, okay, the vision that we had in mind at the beginning when we started talking about reducing the drag. So this is now the movie. You see, of course, the flow field, and now we start after some seconds, you see the movement of the upper surface, and the CD is reduced. We just more or less reduced the size. And when you turn it off, CD comes back again. So this is what we had in mind in the beginning. And we started out working on it by considering, say, the boundary layer, a turbulent boundary layer, of course, over a flat plate. And in the beginning, we considered the surface to be perfectly smooth. So, and today, I'm only going to talk about the results that we computed. So only our numerical analysis will be talked about. Use the code that we developed over the last, let's say, something like 15 years or so. So we performed large eddy simulations, that is, and the method is based on the Miles approach, and the overall, you can say the overall accuracy of that code is second order accurate in time and space. And of course, we also consider something like, let's say, an ALE formulation, because we also have to take into account definitely moving meshes, because otherwise, okay, we cannot realize something like, let's say, the movement of the surface of our airfoil. So this is a very, very brief description of our numerical method. So, and what does the computational domain look like? You see here a sketch of that computational domain. We do have the flow from the upper left to the lower right. We do have in the beginning here, near the leading edge, more or less, okay, we do have a classical flat plate. Then we do have a transition region where we move more or less, okay, from the non-moving part to the moving part. And the moving part is indicated here by that kind of wave. We do have periodic boundary conditions on the left and on the right side. And of course, when you consider what is going on downstream, we also use some kind of, let's say, sponge layers in order to damp some reflections. So I consider that more as a very, very classical description of the numerical flow problem. So, and what I'm going to do is I'm going to talk about a variation of the amplitude of our wave. When you consider, say, that kind of wave, of course, it's described by the amplitude, for example, the wavelength, and also the period. And over the next couple of slides, I'm only going to change the amplitude of the wave that we introduced with respect to the movement of the surface. So we just talk about varying A plus. So this is the amplitude in inner coordinates. And we vary it between 0. That means, okay, we don't consider, say, any movement of the surface. And then we increase it by, let's say, we increase it up to an amplitude value of 70. So the Reynolds number, based on the momentum thickness, this Reynolds number is fixed, and also the period, and also the wavelength is fixed so that we do have, let's say, a constant wave speed. So what does the solution look like when you consider, for example, the mean velocity distribution? This is shown here, and the non-actuated part, so the classical distribution, everybody knows what that classical distribution looks like, is shown by this solid black line. And you can see it here. And then when you consider, say, the red and the blue part, those distributions, they belong to the actuated flat plate, and the red part belongs to the crest. Let me go back. So when we do have here our wave, we do have here the crest, and here we do have the trough part of that wave. And you see, okay, that compared to the non-actuated distribution, there is not that much of a difference between, say, the moving surface and the non-actuated, the non-moving surface. However, when you consider what's going on in the trough region, and that is true for the mean velocity distribution, then you see quite a difference with respect to the non-actuated distribution. And this is also true, of course, when you get closer and closer to the wall, you do have quite a difference with respect to the velocity gradient near the wall. So also when you do consider, say, the stress distributions, so the RMS value of the streamwise velocity component, to be more precise, the fluctuation of it, you see an interesting development. Once again, the black line shows you the distribution of the non-actuated case. And then you do have, let's say, once again, the red and the blue distributions, and they belong to the distributions near the crest and near the trough. And you see quite a decrease with respect to the amplitude when you increase the amplitude of the wave. So A70 reduces that stress distribution, let's say, much stronger than, for example, considering an amplitude of just A plus equal 10. So that means you increase the amplitude and then you gain a lot with respect to the velocity and the shear stress distribution. The same is true when you consider, for example, the vorticity vector, and you consider, say, the component in the normal direction, so normal to the wall, of the vorticity vector. And that omega y distribution is fantastic in the sense that you do have, let's say, a drastic decrease of that kind of distribution in the crest region, and you do have quite a shift, let's say, off the wall when you consider the distribution. Once again, I'm talking about the blue distributions here, okay, when you increase the amplitude. So now it would be pretty simple to conclude that you just change the amplitude, you make it bigger and bigger, and then you gain something, at least with respect to the velocity distribution, and also then something with respect, not only with respect to the wall shear stress, but also with respect to the overall drag. However, this is not the case, because when you consider, for example, the wall shear stress distribution, tau sub W for the non-actuated case, and you compare it to the actuated case, and you want to compute, of course, the drag reduction, you do have to consider, say, the integration over the surface. And when you increase the surface by increasing the amplitude, you lose something, of course, because you simply increase the surface, and that means that does have an impact on the drag reduction. And this is shown here when you consider, say, the upper diagram that shows you the gain with respect to, let's say, drag reduction as a function of time when you let it run, when you do the computation as a function of time. And what you see here is, for example, the solution that you get for an amplitude of A plus equal 10. That is shown here by the dashed line. So this is the lower dashed line. Then you increase the amplitude. Fine, okay. This is the other dashed line. And that belongs to an amplitude of A plus equals 30. And here, of course, okay, then the drag reduction is increased. Fine. But then when you do that, again, and you increase the amplitude from A plus equals 30 to 50, then you lose something, because of course then the surface gets bigger and bigger, and then you don't gain anything, you lose actually something. Why do I let you know that? So I just want to let you know, okay, that it is not that simple. You just go ahead and increase the amplitude and then everything is going to be fine. No, this is not the case. You do have, of course, let's say other effects that you do have to take into account. And I also was only talking about, say, varying the amplitude. Now you can imagine when you also vary now the wavelength, and when you also do vary the period, that then the complete, let's say, picture gets more and more complicated. Nevertheless, okay, let's go back to the amplitude part. And now what we did, instead of only, let's say, considering the case for a smooth flat plate, which is indicated by this sketch here, we also thought, hey, why not do we combine some kind of, let's say, passive drag reduction idea with our active drag reduction idea that was, let's say, the moving surface. And the passive part, of course, has something to do with the riblets. So we thought we consider, say, a structured surface and then use the structured surface and also let it move, okay? Let it undergo a transversal span-wise traveling wave. And of course, we resolved everything also within the riblets. So when you consider, say, the mesh that was, let's say, a highly resolving mesh, so that we could resolve all the details, even, okay, when we consider, say, a moving surface. And what I show you next is the result, for example, for A plus equals 10, and then we also increase it to an A plus equals 30. So just to let you know, okay, what more or less, okay, the solution looks like. This is here for the smooth plate, and this is for the structured surface. And this is the wave direction, which is shown here by the arrow. And the mainstream, the main flow direction is perpendicular to the plane that is shown here on the slide. And you see once again, of course, that we do have, let's say, quite an impact on the flow field in the crest and in the trough region. And you also see that there is hardly any difference with respect to the flow structures. What is shown here is the span-wise velocity in this region, okay, that is described by the riblets. By the way, those riblets, they do have, let's say, an optimized size with respect to a non-moving plate. So for example, when you consider, say, the S plus of the riblet structure is in the range of, let's say, 15, 16 or so, which is something like optimum with respect to the drag reduction that you can expect. And now I show you what it means, for example, when you consider once again the distribution of the normal component of the vorticity vector. Once again, the black line shows you the result for the non-smooth, for the smooth, non-actuated surface. So the classical distribution. And now when you consider, say, the actuated part with a riblet, which is shown here by the red line, you see once again a drastic reduction with respect to the amplitude, and also, let's say, a movement as far as the location of the maximum is concerned, okay, with respect to the surface itself. So more or less, okay, what you observe for the riblet structure is comparable to what you observe with respect to the smooth surface. And then when you do the analysis once again for the complete drag production, not just, let's say, for one quantity, this is shown here once again, sorry. Let me go back to this definition of the drag reduction. Here once again, the wall shear stress for the non-actuated and the wall shear stress for the actuated part. And you do have, let's say, lots and lots of distributions here in the upper diagram. You don't have to go through all those distributions. What is interesting is the following. You consider, say, the data which are listed here on the lower right. And you see that when you only consider, for example, non-actuated riblet surface, you already get a drag reduction in the range of 9%. So when you can now use some kind of movement, so you consider, say, a smooth surface with an amplitude of A plus equals 30, then you get a slightly higher drag reduction that is in the range of 11%. So this is a smooth surface actuated, compared to a riblet surface, non-actuated. So non-actuated, you already gain 9%. And now when you now combine the smooth part and the riblet part, you go from 11% drag reduction to 11.6 drag reduction, more or less nothing, when you combine the smooth and the riblet surface and you let it undergo an actuation. So what we concluded more or less, okay, for this simple analysis was the following, that it is really not worth to consider, say, a riblet structure for this simple case at least. That was the reason why the following analyses were performed only for a smooth surface. Nevertheless, okay, you already saw that, of course, it is quite a parameter space that you do have to span in order to understand what is going on with respect to, let's say, the drag reduction mechanism. So, and therefore, we thought we do have to use something else in order to increase the number of solutions, quote unquote, that we can use in order to come up with a perfect, quote unquote, perfect setup to reduce the drag for a more relevant case, not just for the flow over a flat plate. And that was the reason why we talked about, let's say, developing a reduced water model. So like I said before, we performed a couple of computations in our solutions. Was there a question or so? Because, okay, No,
I think someone just had their mic unmuted. Sorry, Wolfgang.
Oh, okay. Okay. So I just let's say move on, right?
Yeah.
So okay, we do have once again here, say, the movement of the surface, and like I said before, we varied the amplitude, but we also varied the wavelength. We also varied the period, and we performed a couple of computations, and those computations, they are not for free. Of course, there is quite a computational effort you do have to plug in order to do those computations. And that means, like I said before, that we had to come up with another idea in order to really understand what is going on. For example, when you consider, say, just say the variation with respect to the friction coefficient as a function of our wavelength. So you see that we changed the wavelength of our wave between, let's say, values 0, no actuation, up to 3000. And then you see quite a distribution of the solutions with respect to the friction coefficient. So that picture here is not extremely clear. It is very diffuse. That picture gets somewhat clearer when you use another kind of, let's say, illustration for the friction coefficient. For example, what is shown here on the lower right is the friction coefficient, better say the difference with respect to the non-actuated case, as a function of another quantity, and the quantity is nothing else but the ratio of the maximum amplitude of the movement of the surface and the thickness of the Stokes layer. And then you see some kind of linear behavior, especially in the region for a lambda plus greater than 1000. This here definitely has something like, let's say, linear increase. That kind of illustration goes back to Mayama and Fukagata. They came up with the idea to use that kind of ratio, like I said before, okay, the ratio of the maximum amplitude of the movement of the wall and the thickness of the Stokes layer. And then we also used this idea here and combined it with our, let's say, greater solution space. And the enlarged solution space was based on some kind of, let's say, intelligent interpolation. So we had to come up, like I said before, with a solution space which is not only covered by 80 solutions. I mentioned 81 solutions that we have performed before. So in order to do, let's say, an intelligent interpolation, we use what is called support vector regression. This is a very, very powerful regression algorithm from machine learning. And based on that, we developed what is called a ridge line. And the ridge line is nothing else but our quote unquote reduced order model. So what is it? What do we understand when we talk about the ridge line? You do have to understand, okay, that for example, when you consider, say, a fixed wavelength, here you see, okay, nothing else but the variation of the wavelength, lambda plus, and we just fix the wavelength, for example, lambda plus equals 2000, and then you try to find an optimum as a function of the amplitude and of the period. And you do that, okay, for various wavelengths. And then you combine, say, the maxima of the various wavelengths, which are a function of A plus and T plus, and you combine, you link the various maxima, and then they look like, let's say, a pearl necklace, and this pearl necklace is nothing else but the ridge line. And based on that ridge line, let's say, function that we had, we were able, for example, to extend, of course, also our solution space. For example, what we did, we used that kind of ridge line and predicted the drag reduction, for example, for a range of a lambda plus of 5,000. And then we came up with a drag reduction value in the range of, let's say, 30.5%. That was done for a flat plate. And then we combined, okay, that kind of solution with our LES analysis. So what does it mean? We used lambda plus equals 5,000, plugged in the relevant A plus, so the relevant amplitude, plugged in the T plus, and then we simply checked whether or not that kind of drag reduction that we predicted based on our model, that kind of drag reduction was also verified by the large eddy simulation solution. And that was the case when we did it, for example, for this point here, where we predicted 30.5% drag reduction. Then the LES told us, okay, you do have 31% drag reduction. So we were pretty close and we were satisfied with that. And then we used that kind of philosophy in order to have, let's say, more and more data for our solution space. And based on that, we developed, say, the method in order to reduce the drag for the airfoil flow. And we considered two airfoils, like I said before, the DRA and the NECA airfoil. And the various pressure coefficient distributions for the DRA and for the NECA airfoil, they are shown here, say, in the lower part of the slide. So you do have, let's say, a drastic variation of the pressure distribution. The DRA was designed for a transonic flow. The NECA part here, okay, has much, let's say, stronger pressure gradient here on the suction side compared to what you observe here for the DRA airfoil. And we just thought, okay, it makes sense to consider, say, two completely different airfoils and to figure out, okay, whether or not we can use that kind of, let's say, traveling wave movement in order to lower the drag. What you see here on the upper part of the slide is nothing else but quote unquote the computational setup. So we do have the airfoil and we had a surface which was moving, let's say, between 20% chord and something like, let's say, 95% chord. And we considered always a Reynolds number based on the chord length in the range of 400,000. And the DRA and the NECA profile, they were computed for a Mach number of 0.1 and 0.2, 0.2 for the DRA, and the NECA had a Mach number of 0.1. And the angle of attack for the DRA was 2 degrees, and for the NECA was 5 degrees. And what you see here is for the different airfoils, the NECA airfoil is shown in blue, and the DRA airfoil is shown in red. You see the setup for the lambda, for the wavelength, for the period, and for the amplitude as a function of, you can say, the chord length. And it is shown here, okay, the variation of the different quantities in inner coordinates, and the friction velocity is based on the non-actuated case. And you see the various distributions, of course, okay, for the airfoil, for the NECA and the DRA airfoil. So we use that kind of setup to perform the computations. And before I'm going to talk about the results of the computations, once again, I show you here, okay, what it looks like when you see the flow field over that kind of wing section. We defined, of course, the lift and drag coefficients, which of course were determined by integration over the whole surface. And we considered, of course, also the pressure part and also the shear stress part in order to determine the overall force. And when we considered, for example, the drag, we considered the part in the streamwise direction, which is represented by the subscript X here. That is nothing else but to denote, okay, the streamwise direction. So we consider, say, the overall drag, and we also consider, say, the viscous drag when we only consider, say, the viscous forces. And of course, we also determine, because okay, when you consider the flow over an airfoil, you're also interested, of course, in the lift coefficient. And what else did we do? We also determined some kind of, let's say, of net power saving. So this is defined here. When you consider, say, the P sub D, it represents nothing else but the power that is necessary to compensate, of course, okay, the effect of the pressure and the viscous forces. And when you do have the subscript ref here, that means that belongs to the non-actuated case. And that has to be compared to what you observe for the actuated case, which is denoted then here by the subscript act for the P sub D. And we also have to take into account the P sub control, so the power that is necessary to ensure the movement of our surface, and that is defined by the velocity, of course, of our moving surface and the various pressure and shear stress forces that act on our surface. So this is our definition in order to determine the net power savings. And let me go back to this slide here, because here I already mentioned some kind of net power saving that we achieved, for example, when we did the analysis for a simple flat plate flow, and that was in the range of 10%. But what is interesting, of course, okay, that we also gained something, not only for the flat plate flow, but also for the flow over the DRA and the NECA airfoil. I come back to this point later on. So this is now the solution here for the DRA airfoil. And you see here, the upper part is nothing else but the total drag. Then we do have the viscous drag, and you do have the lift here. What is shown is the variation as a function of time. The black line shows you the solution for the non-actuated case, and the red line shows you the solution for the actuated surface. First, what we perform is an analysis for the non-actuated surface, and then we start, after some time, we start the actuation. You see here the transition, and that is, let's say, in the range of, let's say, roughly 6 periods of the movement, or roughly 1/4 of the flow over times. You see the drag reduction then, and then it stays stable for the total drag, for the viscous drag, and for the lift. And you see that we gain something, not only with respect to the total drag, but also with respect to the viscous drag. And what is also interesting is that the lift is increased. You see, by the way, that the transition phase for the lift is much more extended than for the drag part. That has something to do, of course, okay, with the information models, okay, that has to, quote unquote, propagate upstream from the trailing edge of the airfoil to this, let's say, region where we do have then, let's say, the complete actuation. So the same is true also for the NECA airfoil. We do have, once again, total drag. We do have a nice drag reduction for the overall drag, also for the viscous drag, and the lift is also increased. Well, what is nice? let's have a look at the numbers. Before we look at the numbers, I show you here the results for, say, the skin friction distribution for the DRA and the NACA airfoil. That you see when you compare the non-actuated and the actuated case, it doesn't matter whether you consider, say, those distributions for the DRA or for the NACA airfoil. You see by simply comparing black and red, that red is always, let's say, below the black distribution, and that means, okay, that of course you do have, let's say, a drastically lowered skin friction distribution. And this is true not only for the DRA, but also for the NACA airfoil. And now the numbers, okay, that I already talked about, that I already mentioned before, when you see the summary that you do have, let's say, drag reduction for both airfoils in the range of 8%, you always gain something also as far as the lift is concerned. And of course, that means when you consider, say, the ratio of lift over drag, you gain something. And what is also interesting is that when you consider, say, the net power saving, yes, you also gain, for example, for the NACA airfoil, for the NACA 4412, you gain something in the range of 2% net power saving. And I gave you the definition of our net power saving before. Now let's talk about, let's say, some details of the velocity distribution. For example, okay, what is shown here is nothing else but the momentum thickness as a function of chord. You see the reduction of the momentum thickness because once again, the red distribution here shows you the distribution for the actuated case, and the solid black distribution shows you the result for the non-actuated case. You see the reduction, which is distributed over the complete chord length. This is not only true for the DRA, also for the airfoil with a much, much stronger pressure gradient, for example, on the suction side. When you also consider, say, what the flow field looks like, let's say, in the near wall region, what is shown here is nothing else for the suction side, okay? The, let's say, low and high speed streaks, which are indicated here by a value in blue for the U plus equals -3 and the red U plus equals +3. You do have the distribution for the non-actuated case here in that area on the suction side. And when you compare it with the actuated solution, you see that the distribution for those streaks is less intense, you can say, it's less pronounced for the actuated case compared to the non-actuated reference case. And the same is true, of course, when you do that, when you do the comparison for the pressure side, you do have for the non-actuated case a completely different picture compared to the actuated case. It's interesting to see, let me go back, that you do have, when you consider that kind of illustration, widening in the span-wise direction, okay, for those flow structures. Now, we also consider, say, the Reynolds stress distributions, and we do that once again for the DRA and for the NACA airfoil, and we do that at a certain position, and the position is defined here, x over c 0.5. So 50% downstream of the leading edge for the DRA and for the NACA airfoil, and we compare our solution with respect to the non-actuated reference case, which is once again shown by the black solid line. The red part shows you the distribution, for example, of the tangential velocity distribution, and also for the normal and for the span-wise velocity distribution. First, let's talk about the normal distribution. You see the normal distribution, which is indicated here for the actuated case, and you compare it with the distribution for the non-actuated case. There is not that much of a difference, but no, sorry, let me go back to the tangential part of the velocity. There you do have quite a difference. Now, what does it mean when we consider, say, here, this, let's say, band around the dashed line? So that band belongs to the various distributions that you get when you consider, say, the crest and the trough region of your wave. So that just shows you the bandwidth of the various solutions that you get. Consider, say, the different locations for the wave that is moving. So that was the part for the Reynolds stresses, and now here the shear stresses. Once again, you see, of course, quite a variation with when you consider, say, the comparison between the non-actuated reference case and the actuated part. So you simply gain something. And now what is interesting, when you consider, say, the vorticity distribution, and the vorticity distribution here is shown for the various components of the vorticity vector. What is shown here is the fluctuation of the wall normal vorticity vector. And this is the part that you can see here on the in this lower distribution, which I show here by the arrow, and you compare it to the non-actuated case. And there is quite a difference for that kind of distribution. And it was already shown by Jimenez and Pinelli that when you do have, let's say, a lowering, for example, of that quantity, then that means, okay, that you have, let's say, a lower skin friction distribution, that you don't have, let's say, a lower wall shear stress distribution. However, what you see here is the distribution in the near wall region for the tangential component of the vorticity vector. And here you see quite a difference between the non-actuated and the actuated case. So that kind of, let's say, quantity is quite, the difference for that quantity is quite drastic. Once again, it shows you that you do have a widening of the flow structures in the near wall region due to the movement of the surface, to be more precise, due to the movement of the surface in the span-wise direction. This is, of course, true not only for the DRA, but also for the NACA airfoil, what you see here. And that kind of widening is more or less, okay, the major part that reduces the drag. So that is shown here once again. That was our vision. So that we increase more or less, okay, the movement of the surface. We just, let's say, use that span-wise traveling wave. And of course, okay, when you consider, say, the solution that we obtained, this is shown here for the NACA airfoil, no actuation, and then we turn on the actuation, what you have seen before. Now it's just the movie, and you see the variation of the drag coefficient. And here we talk about the viscous drag. When you turn on the movement, which is indicated by that illustration here, you see the reduction of the drag. So with respect to that kind of illustration, you can say, yes, it works when you use some kind of, let's say, movement of the surface, and you do that in the right wavelength, and you do that in the right amplitude and period range, you gain something, not only with respect to the drag, you also gain something with respect to net power saving that you can actually, let's say, exploit in order to reduce the energy consumption. And let me get very, very brief on what it means when you consider now something like a swept wing, because in general, so nowadays, of course, okay, when you consider the flow over a wing, then you consider, say, a swept wing. What does it mean? That means that the wave is not moving perfectly perpendicular to the streamwise direction. And therefore, we came up with the idea to use some kind of inclination for our wave, such that we can definitely try to approximate such a scenario that is observed for the flow over a swept wing. So we simply changed our computational setup, okay, that I've showed you before, to that kind of setup where we do have a wave that does have, let's say, let me go to the next slide, that does have, let's say, an inclination of the wave with respect to the streamwise direction, which is indicated by the x coordinate. And just let me show you at least 2 slides, okay, with respect to the results that we obtained. Once again, when you consider, say, the flow structure for the non-actuated and the actuated case, and what I show you here is the flow structure, once again, for the U plus equals +3 and -3, And you see once again, when you do have, let's say, the actuation for the perfectly perpendicular case that is indicated by phi equals 0, you do have the variation of those structures in the near wall region. And that kind of variation is slightly, quote unquote, slightly diminished when you increase, for example, the inclination angle. Here we do have an inclination angle of 30 degrees, which is shown here. And what I'm talking about when I write down something like downstream and upstream, of course, let me go back to this slide. The wave can move, let's say, from the lower left to the upper right, or in the opposite direction from the upper right to the lower left. So what it boils down to, yes, you diminish definitely the drag reduction, but you still gain something with respect to drag reduction, even when you consider, say, the impact of an inclined wave, of an inclined traveling wave in the span-wise direction. And you see that here, when you consider the drag reduction, yes, it's reduced as a function of phi. So the delta CD as a function of phi is shown here. And the blue part shows you the part that belongs to the viscous drag and the pressure drag, which automatically occurs when you do have, let's say, an inclination of your wave. That increases with respect to the inclination angle, but nevertheless, the overall drag is still reduced. And let me skip the other slides just to make sure, okay, that I don't talk too long about, say, wavy drag reduction. Maybe this slide, okay, is the last one that I'm going to talk about, okay, with respect to the results. This shows you here the variation of the integral length scale, and we show you here the integral length scale in the span-wise direction as a function of the normal wall coordinate. And you see what it looks like, that integral length scale in the span-wise direction for the non-actuated case, which is shown here by the dashed black line. And when you compare it with the solution for the actuated case, for example, for the fully perpendicular wave, you see once again that stretching in the span-wise direction that I mentioned before. And that kind of stretching, this is our interpretation, has something to do that we reduce the fully turbulent case to some kind of, let's say, transitional turbulent case, okay? And for that, this is the reason why we obtain drag reduction for the various cases that we have analyzed. So let me finally conclude, and let me be very brief with respect also the conclusions. We did an analysis for the smooth surface, and you saw, okay, that yes, when you change the amplitude, you gain something with respect to drag reduction. However, there is no free lunch in the sense, okay, that when you do that, when you have, let's say, too large of a amplitude, then the larger surface more or less, okay, kills the gain with respect to drag reduction. The structured surface tells us, yes, you gain something, but it's not worth it to consider, say, a moving structured surface. But when you use the reduced order model and you apply the various setups for airfoil flow, yes, you can reduce the drag for the flow over a DRA or a NACA 4412 airfoil. Of course, we talked about a certain Reynolds number range, we talked about a certain Mach number range, and it's way too early to generalize, okay, that result for any kind of course, for any kind of flow over an airfoil. And finally, when we did the analysis for the spread waves, we can say, yes, when you do have an inclination of the traveling wave, you still gain something with respect to drag reduction. This is still true. Of course, the whole analysis had to be funded. We needed money to do so. The money came from the German Research Association, okay, and that was given to us, okay, as part of, let's say, various projects. And we did a couple of publications in that area, and the latest publications are listed here. And I'm done. I'm happy to take questions, and I hope, okay, that something interesting was part of the presentation. So thanks a lot for listening.
And thank you, Professor Schröder. That was a really great talk. Does anyone have any questions for yes, we do have a question here from Vishal. Do you want to unmute your microphone and ask your question, Vishal?
Hello, Professor Schröder.
Hi.
I was just wondering about the amount of energy that you would require to practically implement those wavy surfaces and compared to the benefit that we see in drag reduction.
Yeah, let me go back to, I hope you can see the slide. When I talked about the definition of our net power saving. You see here, okay, what we plug in, we consider, say, the pressure distribution, upper and lower part of the surface. And of course, we also take into account what is shown here by that kind of symbol as far as the shear stress distribution is concerned. And then we multiply the whole story by the velocity of our movement. So that when we consider, say, our wave, of course, that kind of wave does have, let's say, a normal velocity component. And this is more or less like here, what is meant by V is the normal velocity component. And that defines, say, the power that is necessary to more or less, okay, ensure the movement of the surface.
But are there any other ways to, to actually see the same improvement in drag reduction without actually having to, implement a dynamic surface? I mean, there could be something else. So how does that compare?
So for example, okay, other people use, and you know that blowing and suction and so forth, okay, that you also can do that in order to try to reduce the drag. This is also fine. However, okay, then it's not that easy because what you do when you consider, say, blowing and suction, you also change sometimes, okay, the thickness, for example, of the boundary layer. And when you do change the thickness of the boundary layer, for example, by blowing, by adding some mass to the overall flow field, you also do something, of course, with respect to the pressure drag. And this is something that does have an optimum somewhere. Yes, the only thing that I would like to say, okay, there are different ways to reduce the drag, and there are different, let's say, I don't know, preferences in certain groups. And I think what is necessary is to understand that finally, we do have to combine more or less, okay, the understanding of what we have to do with respect to the flow field in order to reduce the drag. I do not claim that this is the only possible way or that this is the optimum way to do that. Definitely when you consider, say, the moving part of the surface, maybe you can reach such an interaction by using, let's say, a different kind of interaction based off, I don't know, maybe some kind of, let's say, temperature variation or so. Or you use, let's say, I don't know, what you know that plasma actuators or so. That could also be possible. But here, so far, what was at least interesting to us, that we could gain something for very, very different flow problems. I'm talking not only talking about the flat plate, but I'm definitely addressing the various airfoil geometries that we considered. And that for us was, let's say, very positive.
All right. Thank you.
Thank you.
Sai Darba, you've got a question?
Yeah, hi. Thanks, Professor Schröder, for such an interesting talk. Actually, I had done a master's thesis project where we were looking at airfoil optimization using a joint method. And what we observed was that for the design angle of attack, the optimized shape was not exactly optimal for off-design angles of attack. So I wanted to understand, like, have you done any analysis on like seeing how the off-design performance would be for this study?
So what we have done so far is more or less, okay, what I showed you. We consider, say, just two cases.
Okay.
So, we simply picked because, okay, we have done some computations in that area before. We picked, let's say, the alpha equal 2, alpha equals 5 case for the DRA and for the NACA airfoil. And of course, yes, okay, this is something that we haven't done yet with respect to a joint methods, so that you know something about the gradient, so that you know something with respect to the sensitivity. But the simple answer is no, we haven't done a detailed analysis with respect to the sensitivity of that kind of solution.
Okay.
All right.
Mohammed, you had a question?
Yep, thank you. Thank you for this very nice talk. And on a curved surface, on a diverging part of this airfoil where the drag is already reducing because of adverse pressure gradient, why is it required to reduce the drag even further and even be more prone to separation?
Now, you see, very, very good question. So what we try to do is we try to reduce the overall drag. And of course, what is also interesting is that when you consider, say, the different parts of the airfoil, then, like you said, you do have, let's say, a different distribution of the wash stress. And the major idea is, like I said before, to reduce the wash stress in the sense that you gain something with respect to the overall drag. However, you don't want to reach, let's say, a flow state that is more or less, okay, likely to separate. Even if something like that happens, that you do have, let's say, some kind of, let's say, separation, then from a theoretical point of view, what you can do is the following. Then you simply change definitely the actuation. For example, okay, let's talk about something like, okay, that you do have even transonic flow, and you do have a transonic flow where you do have, let's say, a shock that occurs on the suction side. Then in that area where you do have the positive pressure gradient, you could change the wave just to suppress the likelihood of separation by now increasing the wash shear stress. So the only thing, okay, that I showed you here is that when we plug in that kind of movement, that we can, quote unquote, play with the wash shear stress and also with the overall drag that is observed by the flow over such an airfoil. So it's just, okay, the idea what you can do. It's not the final result for everything.
Yep. Thank you.
Okay.
Rena, you had a question?
Yes. Hello, Professor Schröder.
Hi.
I had a question in your numerical technique part, where you have shown that you are use Runge-Kutta method, 5 stages. So I just want to know how you compute the step size.
What step size? The temporal or the spatial step size?
So to consider the Runge-Kutta method, you consider 5 stages. So when you develop the Runge-Kutta method, I think we need to use a step size to calculate the Runge-Kutta method. So how you calculate this on the Runge-Kutta method, step size?
So when you consider, say, our Runge-Kutta method, okay, it's what we use is a 5-stage Runge-Kutta scheme. Yeah. And of course, when we consider, say, our spatial distribution, then we come up with a simple computation that is done on the back of an envelope in order to figure out, okay, what is, say, the expected wash shear stress. And then we would like to make sure, okay, what is that we can resolve, for example, the viscous boundary layer. And then we more or less determine the step size in the wall normal direction such that we do have a y plus in the range of, let's say, roughly in the range of 1. And then we distribute the whole story, of course, also in the streamwise direction. And then based on our, let's say, and now not on the stability, but then in order to make sure that we do have, let's say, a resolution also for the turbulent frequencies, then that is then the basis to determine the temporal step size.
Oh.
So it's done on very, very fundamental knowledge with respect to simple turbulent flows.
Okay.
And then of course, but this is not done here in this computation. And then of course, it's also adapted automatically, but this is done, let's say, for different kind of, let's say, flow problems, not for this part.
Oh, okay.
I don't know. Did I answer your question?
No. Actually, I wanted to ask, know that do you consider a constant step size to when you're calculating Runge-Kutta method, or what is the step size for your calculation Runge-Kutta method? Because I just saw in your numerical technique slide, you point that you have used a Runge-Kutta method 5 stages. So that means you need to consider a step size in Runge-Kutta method calculation. So I just wanted to know what is the step size? Like, is it constant for all the direction, or how you did the step size?
So the step size in the streamwise direction is different compared to the wall normal direction, is different compared to the spanwise direction.
Oh, okay.
Okay? I'm sorry that I didn't get, let's say, the question right from the beginning.
It's okay. Yeah, thank you.
Marco also had a numerics question. Do you want to unmute and ask your question, Marco?
Yes, thanks a lot. Thanks for the talk, first of all. I also work on kind of drag reduction, but that was a very interesting talk for me. I would like to ask, maybe it's a very boring question, but if you can give some more detail about your resolution and the LES model that you are using, because those simulations are kind of expensive, and of course is something that is it's kind of an important parameter on the practical point of view.
So yes, they are expensive, and this is the reason why I mentioned that we performed only, let's say, roughly 80 computations, and then we talked about, let's say, extending our say the solution space based on that kind of, let's say, quote unquote intelligent interpolation part. And see, when we do the computations, I briefly mentioned that we use the Miles approach. So that means we don't use any wall function. We resolve everything down to the wall. You can say, okay, it's not a large eddy simulation. I would prefer to call it something like, let's say, a direct numerical solution, direct numerical simulation in the near wall region. And then when you consider, say, the outer part, then you can talk about something like a large eddy simulation. So it's highly resolved. Everything is resolved down to, yes, okay, in the near wall region, even down to the Kolmogorov scale. And when we do the computations, we do that on, let's say, HPC system, high performance computing systems. So that belong to the tier 0 level. And they do run more than just a couple of hours.
Yeah,
yes.
Yeah. Yes, of course.
This is true. But okay, because you see, what we thought, okay, is necessary. We do have to understand the details in the near wall region. And more or less, the complete program is fully parallelized, okay? It runs on a couple of thousands of processors. We can do that up to, let's say, a couple of 10,000, 100,000 processors. So this is fine. So, and we do have the opportunity to use huge systems in order to do those computations. Yeah. Marian Albers, who did those computations, I would say, hey, we are free to use the computer whenever we like to do so. And this is fine to us.
Yeah. Yeah, no, sorry, I asked that because I noticed that you have, I mean, I have run some LES of at Reynolds number based on the code at 400,000 using X 5000. And we, after some ponderation, we actually use, basically it's not exactly an implicit LES, but it is a forcing term that acts as if it was an implicit LES. So it basically add a volume force that basically reduce a little bit what is still there because the dissipation is not enough to solve that. And our resolution, I think we decided to have it a little bit finer than what you have shown in the slides. So that was the reason of my question. If yeah, how you have balanced that, but yeah, thanks. Anyway, I think
so yes, of course, I didn't mention it. For example, okay, when you consider, say, the flow over the non-moving part of the flat plate or so,
yeah.
That kind of flow which is turbulent, there we use also a boundary condition which is based on a synthetic formulation of, say, the turbulent flow distribution in order to reduce the computational time that is necessary. So we plug in, like I said before, a synthetic formulation for the turbulent inflow boundary. But let's say this would be another talk. We can do that, okay? This is also something that we did a couple of years ago, and that makes it more efficient. Yes, okay, there are some ingredients that I didn't touch in order to make it all work in a, let's say, reasonable time frame.
Yeah, okay. Yeah.
Okay.
Thanks. Yeah, thanks a lot. Yeah, thanks.
Thank you.
Okay, so thank you everyone for your questions, and thanks once again to Professor Schröder for giving us a very interesting talk today. We're very grateful for that, and we hope to see you all next week. So thank you very much.
Thank you very much, Wolfgang.
Thanks a lot. Thanks a lot.
Thank
okay,
you.
now I can fly back home. Okay, I'm pretty fast.